Hi. All right, now let's talk paleotemperature. How do you know what the weather's like outside? You look out the window. It's a beautiful day outside. How do you know what the weather was like a long time ago? There are ways. A good geologist will be able to tell you, or a geochemist in particular, who do work with atomic composition of the rocks. So let's talk about it. One of the easiest, most prominent ways to estimate paleotemperature is from the oxygen 18 to oxygen 16 ratio. And you can do this in the formation itself. If you've got a formation that's got something like carbonate in there, that's going to be like calcium carbonate. And the oxygens that are part of the carbonate ion are going to contain either oxygen 16 or oxygen 18. And those are actually going to be formed inside the water. And the neat thing is that water molecules with O16 are much more likely to evaporate than water molecules with O18. Significantly more. Let's not say much more, like it can't happen the other way. It does, but yeah. So you get an enrichment of water molecules containing O16 that are then going to become precipitation. And so plants are going to pick those up. And also, they're going to end up in ice caps when we have times in the earth where things are very cold. If you want to look at this little thermometer up here we are in the Carboniferous. That's this really cold period right here. And you can see from the chart, it's actually very similar to the period we're in right now. And then right after the Carboniferous, look what happens as we go into the Permian. You get this just sort of skyrocketing temperature. And this is thought to be one of the big contributors to the Great Dying at the end of the Permian. It was just a massive temperature spike, and it spiked, we think, faster than animals could adapt or move. And so a ton of stuff went extinct. That's not all of the Permian extinction story by a long shot. There's a lot of other interesting facets of that, but we'll cover that later. We've got a separate lecture on this. Um, Now, for bonus points, because remember, rocks can be made of parts of older rocks that are broken down, washed out, that's erosion, and then are then going to be deposited and built up. So, how do you know if your rocks are telling you the correct age? The answer is you want to do this oxygen 16 versus 18 assay on creatures that lived in the water, like foraminifera, things like fusulinids, things like all those other little forams that we were looking for in the microfossils. And so you grind up their skeletons because they led very short little lives and they can be identified very precisely. And so they'll tell you, yeah, what was going on at a very particular narrow time. And you have both the biostratigraphy, you can see what this thing is and how that fits in, and the geochemistry that tells you a little bit about what the temperature was, where this creature was living. All right. And so during low glacial or normal periods when there's not much glaciation on the surface of the Earth, what you'll have is that most of the O16 is going to go up into the atmosphere and then it's going to come right back down and it will end up in the ocean. And you'll have plenty of oxygen 16 floating around in the ocean. And being formed into ocean sediments and little animals that are living in oceans that also contribute to ocean sediments. During high glacial periods where we have lots of standing ice on the land, like we're maybe coming to the end of one of those, and it's going to be a big change if that happens. And it's going to be real bad for a lot of things, probably including us. Yeah. We're going to have a lot of O16 that goes up, and this O16 is going to come down as precipitation. A lot of it's going to end up staying and building up things like modern Greenland, Antarctica, building up that snowpack, making glaciers, things like that. And so a lot of the O16 is going to get trapped on land, which means you're going to have a relatively higher amount of O18 in the water. It's not like this. It's not that the water is mostly this other isotope of oxygen. But there is more of it. There's a significant difference, and you can spot this with geochemistry. You sort the atoms by their mass. So let's look at the history of the Earth, things that have been going on, and what's been happening in terms of temperature. There are lots of other geochemical ways to estimate temperature. This oxygen ratio is one of them. But if there are diagenetic processes that are going to alter the oxygen or swap out those oxygen molecules for something else, then those may not be as reliable. And so you'd have to check the degree of alteration and the type of alteration on your particular specimen before you were able to interpret the geochemical results. So, over time, there have been fluctuations. Things have gone hot and cold and hot and cold. Here we can see the major glacial periods. So on this side, we've got our Cambrian, and the Cambrian was warm to very warm. And then right after the Cambrian into the Ordovician, things just carried on. The climate was fairly stable. But then toward the end of the Ordovician and beginning of the Silurian, you had a massive glaciation. This sort of mid-Ordovician glaciation event is actually a big extinction. This is the point at which all the things that were adapted for really hot temperatures are going to be subjected to a rapidly cooling Earth. And that is also bad. It's not that hot or cold is necessarily bad, it's that rapid change moves faster than biology can keep up. Biology is kind of slow, and when the Earth is going fast, then you get big wipeouts, essentially. And you lose a lot of the things that were holding up different parts of the ecosystem. And that's when you find out, that your ecosystem was dependent on a particular set of organisms that are no longer able to function. As you're going through the Devonian, this is when plants start to get really big, and you're getting a lot of erosion on land, a lot of minerals coming out into the water, which leads to another couple of interesting extinction events here. And you get a sort of a temperature spike, and then right at the end of the Devonian, start of the Carboniferous, bam, another big temperature drop. Then it's going to stay cold throughout the Carboniferous, particularly the later Carboniferous, the Pennsylvanian, which is the area that we tend to collect in this part of Texas. You're going to have a lot of glaciation, and that's going to go on into parts of the Permian. And as the global temperature spikes in the Permian, those glaciers are going to go away. They hold on for a while, but eventually they melt away. Massive sea level rise, massive change in global temperature. Then the Earth's going to fluctuate for a little bit, but without the real high highs or low lows. Toward the end of the Cretaceous, right before the big thing from the sky hits and wipes out the dinosaurs, except for the avians. The non-avian dinosaurs get wiped out very quickly. You see, we were in a very hot period. And after that, potentially because of that cloud and potentially blocking sun, but also a whole bunch of other things, the Earth then goes back into a very cold period, which is where we are now. So we're in one of these cold periods, just in geological terms, like in terms of the age of the Earth. And so now let's zoom in a little bit. All right, if you were to look at, and this is the same graph you get over here, it just flipped around backwards. So this is the more recent periods. This is after the Mesozoic. We're in the Cenozoic. And you can see here we are relatively warm early on. And then we're going down and we're getting colder as we get closer to the present. So these are millions of years. So the last maybe 15 million years, everything has been adapting for very, very cold temperatures, which, this being Texas, it's hard to say that it's super cold right now, but in global terms, it still is relatively cold, even though things are heating up rapidly. In the last 5 million years, you can zoom in, you start to see these cycles. Now, these are the same cycles that are going to drive cyclothems. And so a set of 4 of these 100,000 year cycles, and look at them there. Really nice 100,000 year cycles. That is going to form the 400,000 year cyclothem. As we get into the colder time, you get bigger swings because a tiny swing in temperature means a big swing in the amount of pack ice you get at the poles in particular. So those are going to be really under some stress at the moment. The global temperature, as you can see here, this is the very recent stuff, the anthropogenic change, we think. And it really takes off when technology and smog production and automobiles and factories and all that cool stuff that makes life fun starts kicking in and appears to be changing. The reason we think it's probably us is that there have not been a lot of volcanic eruptions, at least compared to at other times in Earth's history. But there has been a massive increase in greenhouse gases. If you model each of the changes that's coming in at the same time, this is the model for all of these together. You can see the one that's driving most of the increase is greenhouse gases. And so this is us. This is on us. So that's why they're saying we need to reduce carbon dioxide emissions, things like that. These carbon emissions of various sorts. And yeah, it's true because it's doing that. And once we go past a certain threshold, the idea is that there's really no going back. And the best thing we can do is to slow it down to the point where some of the life forms that are around now can start to catch up. Because otherwise, we're just going to crash them and crash the world. Yeah. Now, how do we tell paleotemperature? By looking at rocks, because that's also a thing that can be done. So here are some fascinating, look at these little things. These are fossilized lizard hands. And so these have been done with both drying it out in some sort of plaster of Paris and also applying some pressure. Now that's a thing that where you would need something like a hydraulic press to be operating inside of an oven to create both the pressure of like a big stack of rock being formed on top. Because that's the thing with deposition, it keeps happening. And so there is more and more stuff on top of the older things, and so they get squished. It squishes some of the water out that was in there. It's going to increase the temperature, and the temperature and pressure are going to drive some of those chemical reactions that are involved in fossilization. They're going to make it possible for reactions that wouldn't happen at normal temperature and normal pressure to happen. The heat and pressure are going to act as a catalyst for a variety of cool chemical reactions, many involving nitrogen, that are going to determine fossilization. Yeah. But there's more. There's more. So do you remember conodonts? Here's our conodont animal, that crazy looking little screaming eel with all these little tooth-like elements down in its throat, because these were jawless. They just got sort of a mouth where they could suck onto things and then potentially bore into them with these little teeth. And what we've got here, or they could, I guess, hunt for smaller prey and crunch them up with their teeth. Yeah, it's weird to have teeth without jaws, but that's them. If you look at the conodont elements, though, they will actually tell you the amount of temperature that's happened to these fossils during the period of their fossilization. Because you don't get high heat everywhere, you get different amounts of heat. And you can actually see just from the color of these, like here's a nice little scale. So here they are. If it's been below, let's say, 50 degrees for the entire time, they remain essentially unmodified, just as they were in the animal. So minimal diagenetic change of that sort. And you'll get this color change. It'll go sort of reddish brown and then kind of black. And then when you get to really high temperatures, like around 500 degrees, they're going to start to go white again after they've gone black. And if you get them to higher temperatures than that, they will actually start to go kind of white and powdery, and they just sort of crumble away. And they become very hard to read if they've been subjected to high temperature. So in something like a metamorphic rock, where there's been so much temperature and pressure that even the rock has become completely altered, you would not usually be able to find anything like a conodont element that was still readable. Yeah. Maybe just little traces to show you where they were in lightly metamorphized rock. Can this happen with us now? Oh, you betcha. Yeah. Here's some pictures from a fascinating paper. These are actual human teeth. So this is from actually two different forensics journals. They're looking at what happens to human teeth over time with temperature. And so they're saying, like, if you have a structure fire, house burns down, you can tell how long that corpse was subjected to a certain amount of heat. It's at 300 degrees. You can see the root color starts to change from creamy yellow to brownish black. It burnt at 400 degrees. You can see the whole thing goes kind of gray on the top. We're starting to get some chemical alteration of the dentine of the actual molecular structure. And if you heat these things up to 600 degrees Celsius, and remember Celsius, that's a lot hotter than 600 Fahrenheit, you can see that these things just start to crumble away. The roots will fall apart. The actual crown of the tooth will last a little bit longer, but these get very, very delicate. And if you try to decalcify them, sort of remove the calcite with a little bit of acid, they will just crumble to dust. And here's one that was burned at 700 degrees and didn't quite fall apart, but if you were to tap this thing, it would just disappear. So yeah, it's not just conodont teeth. Someday our teeth are going to do this as well. And I think that's, I don't know, is that reassuring or is that macabre? Hard to tell. So anyway, there's paleotemperature. So in terms of questions, let's think of some questions. So I would like you to be able to walk me through this 016, 018 cycle and what it means. You will notice on the Paleozoic climate change graphs, these sort of global climate graphs are going to be determined right there by the difference in oxygen 18. And so, yeah, those differences are going to show us what the paleotemperature was like. And they're going to be kind of slow moving. The differences in the formation may lag behind the actual speed of the differences happening on the planet. So real life is faster than rocks, as you might imagine. I'd like you to know the major periods of glaciation. It was a little bit in the early Cretaceous, a whole bunch in the late Carboniferous, and from the end of the Ordovician, very cold time. Here's our paleotemperature low point. And then right now, we're in a period of glaciation, but we may be coming out of it. And historically, when we have gone from glaciers to very hot temperatures, the world has suffered. Biology has suffered very harshly. So we'll see if that happens again. Yeah, hopefully not, but probably yes, given the amount of extinction that's going on right now. Okay, and then the other thing to know are these 100,000 year cycles. These are caused by the wobble of the Earth as it goes around the sun. Its orbit is a little bit wobbly, and so there are little tiny 41,000 year cycles that then stack together and make larger 100,000 year cycles approximately. And those also stack on top of each other, so they line up just right about every 400,000 years. And that's what ends up defining those cyclothems that we saw in the Paleozoic in particular. But really, at any time when there are, when there's a cold planet and the polar ice caps are kind of at the edge where they could form up and pull a bunch of water out of the ocean, or completely melt and dump a bunch of water into the ocean, and we're kind of at that intermediate temperature in the yo-yo zone. Which is where we are right now. Yeah. So let's see if there's anything else we really need to do. Anthropogenic climate change, mainly from greenhouse gases, and the modeled climate change is a very good match for what we're actually observing, and which we can see is mostly due to not changes in the sun or ozone or volcanoes or sulfate release, but to greenhouse gases. Then pressure and heat causing diagenesis. Heat in particular being a thing that is going to be indicated by the color of teeth. such as little conodont element teeth. And of course, also human teeth. Yeah, we can simulate the same things. So I think that is a good overview of paleotemperature. I hope that's been helpful, and thank you very much.